How big is the universe really? Welcome back to another episode of Quiet Cosmos. Today we will be exploring one of the most profound questions humanity has ever asked. How big is the universe really? Opening, the question that expands our minds. When we gaze up at the night sky, we see what appears to be a dome of darkness punctuated by points of light. Ancient peoples imagined this celestial sphere as something relatively small and manageable, perhaps only thousands of miles across. Even as recently as a century ago, many astronomers believed that everything we could see existed within a single galaxy, and that this galaxy might constitute the entire universe. How wrong those assumptions turned out to be. Today, we know that the universe is so vastly, incomprehensibly large, that even our most advanced measurements and sophisticated mathematics struggle to capture its true scope. The universe is not just big, it is not merely enormous. Those words fail to convey the reality of cosmic scale. The universe extends so far in every direction that light itself, traveling at 186,282 miles per second, has not had sufficient time since the beginning of everything to reach us from the most distant regions. Think about that for a moment. Light can circle the Earth more than 7 times in a single second. In 1 year, light travels nearly 6 trillion miles. And yet, there are parts of the universe so remote that even after 13.8 billion years of travel, their light still has not reached our telescopes. As we journey through this exploration, we will confront measurements that seem to defy logic, discover structures so large they challenge our understanding of how the universe formed, and peer into theoretical frameworks that suggest our entire observable cosmos might be just one bubble in an infinitely larger reality. This is not a journey measured in miles or kilometers, but in light years, megaparsecs, and concepts that push human comprehension to its absolute limits. The question of the universe's size is not academic or abstract. It speaks to the fundamental nature of reality itself, to the origins of everything we can ever know, and to the ultimate fate of all that exists. As we explore the answer, we will find that the universe is far stranger, far larger, and far more wonderful than we ever imagined. We will discover that in asking how big the universe is, we are really asking what it means to exist in space and time, what lies beyond the boundary of observation, and whether there are limits to what we can ever truly know. So settle in as we venture outward from our small blue planet, past the familiar constellations, beyond our galaxy, through clusters and superclusters, across the vast cosmic web, to the very edge of what can be observed and into the realm of what can only be imagined. The universe awaits, and it is far bigger than you think. The observable universe, our cosmic horizon. Let us begin with what we can actually see, or more precisely, with what we could theoretically observe given perfect instruments and unlimited time. This region of space is called the observable universe, and its dimensions are staggering. According to current measurements, the observable universe has a diameter of approximately 93 billion light-years. To put this number in perspective, a single light-year represents the distance light travels in 1 year, which equals about 5.88 trillion miles or 9.46 trillion kilometers. Multiply that already incomprehensible distance by 93 billion, and you begin to approach the true scale of the cosmic arena that surrounds us. But here is where things become immediately puzzling. The universe, according to our best evidence, is approximately 13.8 billion years old. It began with an event we call the Big Bang, an expansion of space itself from an infinitesimally small point to the vast cosmos we inhabit today. If the universe is only 13.8 billion years old, and light is the fastest thing that exists, traveling at an absolute cosmic speed limit, then how can the observable universe be 93 billion light-years across? Shouldn't the maximum distance we can see be limited to 13.8 billion light-years in any direction, giving us an observable universe with a diameter of about 27.6 billion light-years? This apparent paradox reveals one of the most important and counterintuitive aspects of cosmology. The universe itself is expanding, and has been expanding since the moment of the Big Bang. This expansion is not like the explosion of a bomb, where matter flies outward through pre-existing space. Instead, Space itself is stretching, carrying galaxies along with it like raisins in rising bread dough. When we observe a galaxy that emitted light 13 billion years ago, we are not seeing that galaxy where it was when it released that light. We are seeing ancient photons from a galaxy that, due to the expansion of space, has moved much farther away in the intervening eons. Consider the cosmic microwave background radiation, the oldest light we can detect. This radiation was released approximately 380,000 years after the Big Bang, when the universe had cooled enough for electrons and protons to combine into neutral hydrogen atoms. At that moment, photons could finally travel freely through space without constantly being scattered by free electrons. The matter that emitted this radiation was relatively close to what would eventually become our region of space, perhaps only 42 million light-years away at the time. But those photons have been traveling for 13.8 billion years, and during that entire journey, the space between us and their point of origin has been stretching. The matter that emitted that ancient light has continued to move away from us as space expanded. Today, accounting for this expansion, we calculate that those regions of space now lie approximately 46.5 billion light-years away from us in every direction. This gives us our observable universe with a radius of 46.5 billion light-years and a diameter of about 93 billion light-years. The light we see comes from the past, but the objects that emitted that light exist in a much more distant present. This observable universe is often described as a sphere with Earth at its center, but this geocentric view is misleading. Every point in the universe has its own observable sphere, its own cosmic horizon defined by the distance light could have traveled to reach it since the Big Bang. An observer in a galaxy billions of light-years away would see their own observable universe, overlapping with ours in some regions, but extending into space we can never observe. The observable universe is not a universal property, but a local one, defined by our particular location in space and time. The boundary of the observable universe is called the particle horizon or the cosmic light horizon. It represents the maximum distance from which light has had time to reach us since the beginning. Beyond this horizon lies a region we simply cannot see, no matter how powerful our telescopes become. Those photons have not yet had time to complete their journey across the expanding cosmos. As time passes, our particle horizon will expand, and we will theoretically be able to see light from increasingly distant regions. However, the accelerating expansion of the universe complicates this simple picture, as we shall explore later. Within this 93 billion light-year sphere lies everything we can ever hope to observe. Every galaxy, every star, every planet, every photon of light that has reached us or will ever reach us. The observable universe contains, by current estimates, somewhere between 100 billion and 2 trillion galaxies, each containing hundreds of billions to trillions of stars. The total number of stars in the observable universe likely exceeds 10 to the power of 24, a number so large that it dwarfs the count of all grains of sand on all the beaches of Earth. Yet for all its immensity, the observable universe represents only what we can see. The actual universe, the total extent of space and matter and energy, almost certainly extends far beyond this boundary. The observable universe is like an island of light in a potentially infinite ocean of space, an island whose shores are defined not by the edge of reality, but by the limitations of light speed and cosmic time. The expansion of space, a universe in motion. To truly understand the size of the universe, we must first grasp the profound discovery that revolutionized cosmology in the early 20th century. The universe is expanding. This revelation fundamentally changed our understanding of cosmic scale and continues to shape our conception of how big the universe really is. The story begins in the 1920s with astronomer Edwin Hubble, working at the Mount Wilson Observatory in California. Using what was then the world's largest telescope, Hubble made observations that would forever alter humanity's cosmic perspective. He studied objects called Cepheid variable stars in what were then called nebulae, fuzzy patches of light whose nature was hotly debated. By carefully measuring the brightness and pulsation periods of these stars, Hubble determined that many of these nebulae were actually enormous galaxies far outside our own Milky Way. But Hubble's most revolutionary finding came when he examined the light from these distant galaxies. When light passes through a prism, it spreads into a spectrum of colors, each wavelength creating a distinct line. By studying the spectra of distant galaxies, Hubble noticed something extraordinary. The spectral lines were shifted toward the red end of the spectrum. This redshift indicated that these galaxies were moving away from us. Moreover, the farther away a galaxy was, the faster it appeared to be receding. This relationship, now known as Hubble's law, revealed that the universe is not static but expanding. Galaxies are not simply flying through space away from us. Rather, the space between galaxies is stretching, carrying them apart like dots drawn on an inflating balloon. When we measure the redshift of distant galaxies, we are measuring how much space has expanded during the time it took for their light to reach us. The rate of this expansion is quantified by the Hubble constant, denoted as h sub 0. This value tells us how fast the universe is expanding at the present epoch. Current measurements place the Hubble constant at approximately 67 to 74 kilometers per second per megaparsec, though there remains some disagreement between different measurement methods. What does this mean in practical terms? It means that for every megaparsec of distance, roughly 3.26 million light-years, galaxies are receding from each other at a velocity of about 67 to 74 kilometers per second. This might seem like a modest speed, but it accumulates with distance. A galaxy 1 billion light-years away is receding from us at roughly 22,000 kilometers per second, about 7% of the speed of light. A galaxy 10 billion light-years away is receding at more than 220,000 kilometers per second, or about 73% of light speed. At sufficient distances, the recession velocity actually exceeds the speed of light. This does not violate Einstein's special relativity, which prohibits objects from moving through space faster than light, because this motion is not through space, but rather the expansion of space itself. The expansion of the universe has profound implications for cosmic size. First, it means that the universe was smaller in the past. If we run the clock backward, the galaxies converge, and the universe contracts until, approximately 13.8 billion years ago, all matter and energy occupied an infinitesimally small region of space. This is the Big Bang, not an explosion in space, but an expansion of space itself from an initial singularity. Second, the expansion affects how we measure distance on cosmic scales. Astronomers distinguish between different distance measures. Light travel distance is simply the distance light has traveled to reach us, which for the most distant observable objects is approximately 13.8 billion light-years. But the proper distance, or comoving distance, accounts for the expansion that has occurred during the light's journey. This is why we say the observable universe is 93 billion light-years across rather than just 27.6 billion light-years. Third, and perhaps most intriguingly, observations made in the late 1990s revealed that the expansion of the universe is accelerating. Two independent teams studying distant supernovae discovered that these stellar explosions appeared slightly dimmer than expected, indicating they were farther away than simple expansion models predicted. This acceleration implies the existence of a mysterious component called dark energy, a form of energy that permeates all of space and exerts a kind of anti-gravity, pushing the universe to expand ever faster. Dark energy is now believed to constitute approximately 68% of the total energy density of the universe. Dark matter, an invisible form of matter that interacts gravitationally but not electromagnetically, accounts for about 27%. The ordinary matter that makes up stars, planets, and everything we can see constitutes only about 5% of the cosmos. This means that the vast majority of the universe's content is made of substances we cannot directly observe and do not fully understand. The accelerating expansion driven by dark energy has profound consequences for the ultimate size and fate of the universe. As the expansion accelerates, distant galaxies recede faster and faster. Eventually, galaxies beyond our local gravitationally bound cluster will accelerate away so rapidly that their light can never reach future observers. There is a future cosmic horizon beyond which galaxies will become forever inaccessible, even in principle. The observable universe in the far future will actually shrink in terms of the number of galaxies it contains, even as space continues expanding. Understanding cosmic expansion is essential to grasping the universe's size, because expansion determines what we can see, how we measure distances, and how the cosmos has evolved from its compact beginning to its current vastness. The expansion also hints that the universe may be far larger than we can observe, with regions of space accelerating away from us so rapidly that we will never receive light from them, no matter how long we wait. Counting the contents, galaxies beyond number. Within the observable universe's immense volume, matter has organized itself into structures of stunning complexity and scale. To comprehend the size of the universe, we must attempt to count its contents, to enumerate the islands of stars that populate the cosmic ocean. This census reveals numbers that challenge our ability to grasp their magnitude. For most of human history, we had no concept of galaxies as separate structures. The Milky Way itself was poorly understood, and the fuzzy patches visible in telescopes were thought to be nebulae within our own cosmic system. It was not until the 1920s that Edwin Hubble's observations of Cepheid variables in the Andromeda Nebula proved that it lay far outside the Milky Way, a separate galaxy in its own right. As telescopes improved throughout the 20th century, astronomers began the challenging task of estimating how many galaxies exist in the observable universe. Early counts were necessarily limited, sampling small regions of sky and extrapolating to the full celestial sphere. In the 1990s, the Hubble Space Telescope provided a revolutionary tool for this census. Astronomers pointed Hubble at what appeared to be an empty patch of sky in the constellation Ursa Major, a region so devoid of obvious objects that it seemed to contain nothing at all. What Hubble revealed was staggering. In that tiny patch of apparently empty sky, a region no larger in angular size than a tennis ball viewed from 100 feet away, the telescope detected approximately 3,000 galaxies. Each galaxy contained billions or trillions of stars. Each represented an entire cosmic system comparable to our own Milky Way, yet so distant that it appeared as merely a faint smudge of light, even to our most powerful instruments. This observation, called the Hubble Deep Field, revolutionized our understanding of galactic abundance. Astronomers refined the observation in subsequent years, creating the Hubble Ultra Deep Field and then the Extreme Deep Field, each reaching deeper into space and time, each revealing more and more galaxies packed into what had seemed like cosmic voids. Based on these deep field observations and statistical extrapolation, astronomers in the late 1990s estimated that the observable universe contained approximately 100 to 200 billion galaxies. This number alone is difficult to comprehend. If you attempted to count every galaxy in the observable universe at a rate of 1 galaxy per second, working continuously without pause, it would take you somewhere between 3,000 and 6,000 years to complete the task. But even this staggering estimate proved to be too conservative. In 2016, a team led by Christopher Cancellis at the University of Nottingham undertook a more sophisticated analysis. They created three-dimensional models from Hubble images and applied new mathematical techniques to account for galaxies too small, too faint, or too distant to be directly observed. Their conclusion upended previous estimates. The observable universe contains at least 2 trillion galaxies, 10 times more than earlier calculations suggested. This revision did not mean that 10 times as many galaxies had suddenly appeared. Rather, it reflected our improved understanding that the early universe contained many more small, faint galaxies than we had realized. Over cosmic time, these dwarf galaxies merged and combined to form the larger galaxies we observe today. The total number of distinct galactic systems has actually decreased over time through mergers, but accounting for all the galaxies that have ever existed brought the total to this astonishing 2 trillion figure. However, even this number remains uncertain and continues to evolve. A 2021 study using data from NASA's New Horizons spacecraft, which has traveled beyond the bright zodiacal light of our inner solar system, measured the total background light in several patches of sky. By accounting for how much light galaxies would need to produce to create this glow, the study suggested the galaxy count might be lower than 2 trillion, perhaps only 100 to 200 billion galaxies after all. The discrepancy highlights how challenging it is to conduct an accurate census of the cosmos. What is certain is that the number of galaxies is enormous, and within each galaxy reside hundreds of billions to trillions of stars. The Milky Way alone contains an estimated 100 to 400 billion stars. If we conservatively estimate 100 billion galaxies with an average of 100 billion stars each, we arrive at 10 billion trillion stars in the observable universe, a number written as 10 followed by 22 zeros. More generous estimates put the number at 10 followed by 24 zeros, exceeding the total number of grains of sand on all Earth's beaches. But galaxies are not uniformly distributed through space. They cluster together in groups and clusters, which themselves form even larger structures called superclusters. Our Milky Way belongs to the local group, a collection of more than 50 galaxies dominated by the Milky Way and the Andromeda Galaxy. The local group, in turn, is part of the Laniakea supercluster, a structure spanning 520 million light-years and containing the mass of approximately 100,000 trillion suns. The sheer abundance of galaxies tells us something profound about the universe's size. These trillion or 2 trillion galaxies are spread across the 93 billion light-year diameter of the observable universe, separated by vast distances. The average distance between galaxies in regions not within dense clusters is millions of light-years. The universe is mostly empty space, with these islands of matter separated by cosmic voids. Moreover, when we look at distant galaxies, we see them as they were in the past. A galaxy 10 billion light-years away appears to us as it was 10 billion years ago. The most distant galaxies we can observe show us the universe when it was only a few 100 million years old, shortly after the first stars ignited. These primordial galaxies look very different from mature galaxies like our Milky Way, smaller and more chaotic, still in the process of formation. The census of galaxies thus provides both a measure of the universe's contents and a history of its evolution. It shows us that the universe has grown and changed over its 13.8 billion year history, that galaxies have formed, merged, and evolved, and that the cosmic landscape we observe today is the product of billions of years of gravitational and electromagnetic processes operating on an almost unimaginable scale. The cosmic web, structure on the grandest scale. When we examine the distribution of galaxies across vast reaches of space, we discover that they are not scattered randomly, but instead form an intricate structure known as the cosmic web. This web represents the largest organized pattern in the universe, and understanding its architecture provides crucial insight into the true scale of cosmic structures. Imagine, if you can, pulling back to view the universe from an impossible vantage point, seeing billions of light-years of space all at once. What you would observe is not a uniform distribution of galaxies, but rather a complex network resembling a three-dimensional spider's web or the neural networks of a brain. Galaxies cluster along thin filaments, like beads on strings, while vast empty regions called cosmic voids occupy the majority of space. This cosmic web structure consists of 4 main components. The densest regions are nodes, which correspond to massive galaxy clusters and superclusters, where hundreds or thousands of galaxies congregate under their mutual gravitational attraction. From these nodes extend filaments, elongated structures composed of galaxies and dark matter that can stretch for hundreds of millions of light-years. Where filaments intersect, they may form sheet-like structures or walls. Between all these structures lie the voids, enormous regions nearly devoid of galaxies, stretching 30 to 300 million light-years across. The filamentary structures are truly staggering in size. Typical filaments extend 50 to 80 megaparsecs, which translates to roughly 160 to 260 million light-years. But some filaments dwarf even these dimensions. The Hercules Corona Borealis Great Wall, discovered in 2013, is a structure measuring more than 10 billion light-years across, making it one of the largest known structures in the observable universe. For comparison, this single structure spans more than a tenth of the diameter of the entire observable universe. Another immense structure, discovered more recently and named Kipu, reaches approximately 400 megaparsecs, or about 1.3 billion light-years in length. These colossal filaments connect clusters of galaxies across cosmic distances, channeling matter and energy along their lengths. The gas within these filaments, though extraordinarily diffuse, contains a significant fraction of the universe's ordinary matter. The cosmic web is not merely a visual association of galaxies, but a real physical structure shaped by gravity and the distribution of dark matter. Computer simulations of cosmic structure formation, which model the evolution of matter from shortly after the Big Bang to the present day, consistently reproduce web-like patterns that closely match what we observe. These simulations reveal that the cosmic web emerged from tiny quantum fluctuations in the very early universe, fluctuations that were stretched to cosmic scales during the inflationary epoch, and then grew through gravitational attraction over billions of years. Dark matter plays a crucial role in the cosmic web. This invisible substance, which interacts primarily through gravity, forms the scaffolding upon which visible matter accumulates. Dark matter halos, invisible cocoons of this mysterious substance, surround galaxies and galaxy clusters. The filaments of the cosmic web are primarily composed of dark matter, with ordinary matter, the atoms that make up stars and gas, following the gravitational contours established by dark matter's distribution. Recent observations have even captured direct images of filaments. Using hundreds of hours of observation time on sensitive instruments, astronomers have detected the faint glow of hydrogen gas flowing along filaments connecting galaxies billions of light-years away. These observations confirm what simulations predicted. The cosmic web is not just a statistical pattern, but a genuine network of matter spanning the cosmos. The voids, those vast empty regions between filaments, are equally important to understanding cosmic structure. These regions are not absolutely empty, but contain far fewer galaxies than average. A typical void might be 100 to 300 million light-years across and contain only a handful of galaxies, compared to the hundreds or thousands found in equivalent volumes within filaments or clusters. The largest known voids span up to 500 million light-years, regions of space so vast that light takes 500 million years to cross from one side to the other. The existence of the cosmic web on such enormous scales tells us something profound about the universe. These structures could only have formed if the universe has certain properties, if it contains specific amounts of dark matter and dark energy, if it began with particular initial conditions, and if it has evolved for billions of years under the influence of gravity. The cosmic web is both a testament to the universe's age and a fingerprint of its initial state. Moreover, the cosmic web illustrates the hierarchical nature of cosmic structure. Matter organizes itself at many scales. Planets orbit stars, stars cluster into galaxies, galaxies gather into groups and clusters, clusters connect via filaments into superclusters, and superclusters form the nodes and filaments of the cosmic web. Each level of this hierarchy emerges from the gravitational influence of dark matter and the expansion of space, creating a nested structure that spans from the scale of planetary systems to the scale of the observable universe itself. The study of the cosmic web continues to reveal new insights about the universe's composition, evolution, and ultimate fate. As our telescopes probe deeper into space and our simulations become more sophisticated, we refine our understanding of how matter distributed itself across cosmic scales and how the largest structures in nature came to be. Beyond what we can see, the unobservable universe. The observable universe, vast as it is with its 93 billion light-year diameter, its 2 trillion galaxies, and its intricate cosmic web, represents only a portion of the total universe. Beyond our cosmic horizon lies a realm we cannot observe, a vast expanse of space and matter that exists beyond the reach of any signal that could have reached us since the Big Bang. The true size of the universe, the total extent of space and all it contains, remains one of cosmology's deepest mysteries. To understand what lies beyond our observable bubble, we must consider what defines that boundary. The observable universe is limited not by the universe's edge, if such an edge exists at all, but by the finite age of the universe and the finite speed of light. Light from regions farther than about 46.5 billion light-years away, accounting for expansion, has not had time to reach us. As time passes, we will in principle be able to see light from increasingly distant regions, but the accelerating expansion of the universe complicates this simple picture. So what exists beyond our horizon? Almost certainly, more of the same. There is no reason to believe that the universe suddenly ends at the boundary of what we can observe. The cosmic microwave background, the most distant light we can detect, shows remarkable uniformity in all directions, suggesting that the universe extends far beyond our view and maintains similar properties across vast distances. The observable universe appears to be a representative sample of the whole, not a special or unique region. But how much larger is the entire universe compared to what we can see? This question has no definitive answer, but cosmologists have developed several approaches to estimating the minimum size. One approach considers cosmic inflation, the period of exponentially rapid expansion thought to have occurred in the first fraction of a second after the Big Bang. Different inflationary models predict different minimum sizes for the total universe. If inflation began about 10 to the power of -37 seconds after the Big Bang and proceeded at close to the speed of light, the total universe today could be at least 1.5 times 10 to the power of 34 light-years across. This is a number so large it becomes nearly meaningless. Written out, it is 15 followed by 33 zeros, making the entire universe at least 3 times 10 to the power of 23 times larger than the observable universe. In such a cosmos, our observable bubble would be an infinitesimally small fraction of the whole, like a single atom in planet Earth. Another approach uses statistical analysis of cosmic structure. Researchers led by Mihran Vardanyan used Bayesian model averaging to analyze various cosmological observations, and concluded that the universe is at least 250 times larger than the observable universe, giving a minimum diameter of about 7 trillion light-years. While substantially smaller than estimates based on inflation, this still represents a cosmos of staggering immensity. Some models suggest the universe might be infinite, extending forever in all directions with no boundary or edge. An infinite universe is actually a common prediction of many inflationary scenarios and is consistent with observations showing that space appears to be geometrically flat on large scales. In an infinite universe, every possible configuration of matter would occur infinitely many times, meaning there would be infinitely many regions identical to our own observable universe, infinitely many versions of Earth, infinitely many versions of you. The geometry of space itself determines whether the universe is finite or infinite. Einstein's general relativity allows for 3 possible geometries: flat, like an infinite plane; positively curved, like the surface of a sphere; or negatively curved, like a saddle. Current observations, particularly of the cosmic microwave background, indicate that the universe is very close to flat, with curvature so slight it cannot be measured with current precision. A perfectly flat universe would be infinite, though a nearly flat universe could still be finite but extremely large. If the universe is finite, it might have a topology more complex than a simple sphere. It could wrap around on itself in strange ways, like a 3-dimensional version of a video game where exiting one side of the screen brings you back on the other. In such a universe, light could potentially travel around the entire cosmos, and we might observe the same galaxies in different directions, seeing them at different epochs in their history. Astronomers have searched for such patterns in galaxy distributions, but have found no convincing evidence. Another profound question concerns whether our unobservable universe has the same physical laws as our observable region. In our observable universe, the laws of physics appear constant. The speed of light is the same everywhere we look. The strength of gravity does not vary with location, and fundamental constants maintain their values. But we cannot know if this holds true beyond our horizon. Some theories, particularly those involving eternal inflation and the multiverse, suggest that different regions might have different values for fundamental constants or even different physical laws. The unobservable universe also raises questions about the ultimate fate of cosmic expansion. Dark energy, which drives the accelerating expansion, appears to have a constant density, meaning that as space expands, the total amount of dark energy increases. This leads to a scenario called the Big Rip in some models, where expansion eventually becomes so rapid that it tears apart galaxies, stars, planets, and ultimately atoms themselves. Other models suggest expansion will continue forever, but at a decelerating rate, leading to a cold, dark, eternally expanding cosmos. What we can say with confidence is that the universe extends beyond our cosmic horizon, that it likely contains far more galaxies than the trillion or two we can observe, and that its total size dwarfs even the immense scale of the observable universe. Whether it is 250 times larger, trillions of times larger, or truly infinite remains uncertain. The universe beyond our view remains, for now, in the realm of theoretical physics and mathematical cosmology, a vast unknown territory that we can model and predict but cannot directly observe. The deep history, from Big Bang to today. To fully appreciate the universe's current size and structure, we must journey back through its history, witnessing the dramatic evolution from an inconceivably hot, dense state to the vast, cool cosmos we inhabit today. This history spans 13.8 billion years, each epoch characterized by different physical processes and leaving its mark on the universe we observe. In the beginning, approximately 13.8 billion years ago, the universe existed in a state fundamentally different from anything we experience today. All the matter and energy that would eventually form hundreds of billions of galaxies, all the space that would expand to create a cosmos 93 billion light-years across, existed in a region smaller than a single atom. The temperature was unimaginably high, far exceeding anything achievable in modern particle accelerators. Space and time themselves emerged from this initial singularity in an event we call the Big Bang, though this name is somewhat misleading since it was not an explosion in space, but an expansion of space itself. In the first fraction of a second, specifically the first 10 to the power of negative 35 seconds, the universe underwent a period called cosmic inflation. During this extraordinarily brief interval, space expanded exponentially, doubling in size at least 60 times in rapid succession. A region smaller than a proton swelled to many light-years across in less time than it takes light to cross an atomic nucleus. This inflation solved several puzzles about why the universe appears so uniform in all directions and why space appears geometrically flat. Inflation also amplified quantum fluctuations, tiny random variations in energy density at subatomic scales, stretching them to cosmic proportions. These fluctuations became the seeds for all structure we observe today. Regions that were infinitesimally denser than average would eventually, through gravitational attraction, become galaxies and galaxy clusters. Regions slightly less dense would become cosmic voids. After inflation ended, the universe entered a period of more gradual but still rapid expansion. For the first 380,000 years, the universe was a hot, dense plasma of protons, electrons, and photons. Light could not travel freely through this plasma because photons constantly scattered off free electrons. The universe was opaque, filled with a brilliant glow but impossible to see through, like being inside a star. Then, as expansion lowered the temperature to about 3,000 degrees Kelvin, a critical transition occurred. Electrons and protons combined to form neutral hydrogen atoms in an event called recombination. Suddenly, photons could travel freely through space without scattering. The universe became transparent, and those photons have been traveling through expanding space ever since. Today, redshifted by expansion to microwave wavelengths and cooled to just 2.7 degrees above absolute zero, they form the cosmic microwave background, the oldest light we can observe. Following recombination, the universe entered the cosmic dark ages. For hundreds of millions of years, space contained only neutral hydrogen and helium gas, slowly collapsing under gravity into the first dense structures. No stars yet existed to illuminate the cosmos. This period lasted until about 400 to 500 million years after the Big Bang, when the first stars ignited, ending the Dark Ages with their ultraviolet light. These first stars were likely very massive, perhaps hundreds of times the mass of our Sun, burning intensely and briefly before exploding as supernovae. Their violent deaths scattered the first heavy elements into space: carbon, oxygen, iron, and other atoms that would eventually become part of planets and life itself. These population 3 stars, as astronomers call them, have never been directly observed, but their existence is predicted by models, and their chemical signatures appear in very ancient stars that formed from gas enriched by their explosions. As the first stars formed, they began reionizing the universe. Their intense ultraviolet radiation stripped electrons from hydrogen atoms, turning neutral hydrogen back into a plasma. This epoch of reionization lasted from about 500 million to 1 billion years after the Big Bang and fundamentally changed the state of intergalactic space, which has remained ionized ever since. Meanwhile, gravity was pulling matter together into larger structures. The first galaxies formed around 400 to 500 million years after the Big Bang. Initially, these were small, irregular collections of stars, much smaller than modern galaxies. Over time, they grew through mergers and continued star formation. By about 1 billion years after the Big Bang, recognizable spiral and elliptical galaxies had begun to appear. The period from 1 to 6 billion years after the Big Bang represents the peak of star formation in the universe's history. Galaxies were actively forming stars at rates far exceeding what we observe today. Our own Milky Way likely formed most of its stars during this cosmic high noon, when the universe was a much more vibrant and active place than it is now. As galaxies evolved, they organized themselves into the cosmic web structure we observe today. Filaments and walls formed along the densest concentrations of dark matter. Galaxy clusters grew through mergers, becoming the massive structures we observe in the nearby universe. Our local group, for instance, formed through the gradual accumulation and merger of smaller galaxies over billions of years. Around 5 to 6 billion years after the Big Bang, approximately when our solar system was forming, something remarkable happened. The expansion of the universe, which had been decelerating due to the gravitational attraction of all matter pulling back on itself, began to accelerate. Dark energy, previously subdominant to matter, became the dominant component of the universe's energy budget and began pushing space to expand ever faster. From that point until today, dark energy has increasingly dominated the dynamics of cosmic expansion. While gravity continues to bind together structures like galaxies and galaxy clusters, dark energy drives apart everything not already gravitationally bound. The universe has entered an era of accelerating expansion that will continue far into the future. Throughout this 13.8 billion year history, the universe has grown from a hot, dense state smaller than an atom to a vast, cool cosmos 93 billion light-years in diameter. The temperature has dropped from trillions of degrees to an average of just 2.7 degrees above absolute zero. The density has decreased from essentially infinite to an average of about 5 protons per cubic meter of space. The universe has evolved from a simple, uniform state to a complex cosmos filled with galaxies, stars, planets, and at least on one planet, life. This history is written in the light we observe. When we look at distant galaxies, we see them as they were billions of years ago. The most distant galaxies appear as small, blue, irregular structures, still in the process of formation. Intermediate distance galaxies show more mature forms, but often display more active star formation than nearby galaxies. The nearest galaxies resemble our own Milky Way, large, well-ordered spirals or ellipticals with much slower star formation rates. The evolution of the universe from the Big Bang to today demonstrates that the cosmos has not always been as large or as structured as it is now. The universe has a history, a narrative arc from simplicity to complexity, from hot to cold, from small to vast. Understanding this history helps us appreciate that the size we measure today is not fixed, but represents a snapshot of an ongoing process of expansion and evolution that will continue for trillions of years into the future. The accelerating universe and its future. The discovery that the universe's expansion is accelerating ranks among the most profound revelations in modern cosmology, and it fundamentally shapes our understanding of how large the universe will eventually become. This acceleration, driven by the mysterious dark energy, determines not only the future extent of the cosmos, but also the ultimate fate of everything within it. The story of this discovery begins in the 1990s, with two competing teams of astronomers studying Type Ia supernovae, stellar explosions so bright they can be seen across billions of light years. These supernovae serve as cosmic distance markers because they all reach nearly the same peak brightness, making them what astronomers call standard candles. By measuring how bright they appear and comparing this to their known intrinsic brightness, astronomers can determine how far away they are. Both teams, the Supernova Cosmology Project and the HiZ Supernova Search Team, expected to find that cosmic expansion was slowing down. The gravitational attraction of all the matter in the universe should act like a brake, gradually decelerating the expansion that began with the Big Bang. The question was simply how much it had slowed. Would the universe eventually stop expanding and recollapse in a big crunch, or would it expand forever but at an ever-decreasing rate? The data revealed something completely unexpected. The distant supernovae appeared dimmer than they should, indicating they were farther away than expansion models with only matter predicted. Instead of slowing down, the expansion of the universe was speeding up. This acceleration appears to have begun relatively recently in cosmic terms, around 5 to 6 billion years ago, approximately the time our solar system formed. This discovery necessitated the introduction or reintroduction of dark energy into cosmological models. The concept was not entirely new. Einstein had proposed something similar called the cosmological constant in 1917, though he later abandoned it. Dark energy, in its simplest form, can be represented by such a cosmological constant, a form of energy inherent to space itself that exerts a negative pressure, essentially an anti-gravity effect. Unlike matter and radiation, which become less dense as space expands, dark energy maintains a constant density. As the universe grows larger, the total amount of dark energy increases proportionally with volume. In the early universe, when matter and radiation were densely packed, their gravitational influence dominated. But as expansion diluted matter and radiation, dark energy eventually became the dominant component. Today, dark energy constitutes approximately 68% of the universe's total energy density. Dark matter accounts for about 27%, and ordinary matter, everything made of atoms including stars, planets, and living beings, comprises only about 5%. The universe is fundamentally composed of substances we do not fully understand, with normal matter being a minority constituent. Nature of dark energy remains one of physics' greatest mysteries. The simplest explanation, Einstein's cosmological constant, treats it as a property of space itself, unchanging in density regardless of how much space expands. Alternative theories propose that dark energy might be a dynamic field called quintessence that can vary in strength over time and space. Other models suggest modifications to general relativity might explain the acceleration without requiring dark energy at all. Observations increasingly favor the cosmological constant interpretation. Measurements of the cosmic microwave background, studies of galaxy clustering, and observations of supernovae all point to a dark energy that behaves very much like a constant. The equation of state parameter W, which characterizes dark energy's pressure relative to its density, appears to be very close to -1, exactly what a cosmological constant would produce. The dominance of dark energy has profound implications for the universe's future size and structure. As dark energy drives acceleration, the universe will continue expanding faster and faster with no limit. Galaxies not gravitationally bound to our local group will recede at increasing velocities. Within about 100 billion years, most galaxies beyond our immediate gravitationally bound cluster will have receded so far and so fast that their light can no longer reach us. Future astronomers in such a distant epoch, if any exist, would observe a universe that appears to contain only their local galaxy cluster surrounded by darkness. This scenario, sometimes called the Big Freeze or heat death, envisions a universe that expands and cools forever. Star formation will gradually decline as galaxies exhaust their supplies of gas. Existing stars will burn out over trillions of years. Eventually, even the longest-lived red dwarf stars will consume their fuel and fade. The universe will grow increasingly dark and cold. On even longer timescales, perhaps 10 to the power of 100 years or more, even the most stable structures will decay. Protons themselves might decay, though this has never been observed. Black holes, the last remnants of collapsed matter, will slowly evaporate through Hawking radiation over timescales of 10 to the power of 100 years for stellar mass black holes to 10 to the power of 100 years for the supermassive black holes at galaxy centers. If dark energy's density remains constant, as current observations suggest, then the universe will literally expand forever, growing ever larger, ever colder, ever emptier. There is no maximum size to such a universe, only an asymptotic approach to absolute zero temperature and infinite volume as time extends toward infinity. However, some more speculative models suggest alternatives. If dark energy is not a true constant, but instead a field that can change, its strength might increase with time. In the most extreme version, called phantom dark energy, the acceleration could become so intense that it eventually tears apart gravitationally bound structures. In this Big Rip scenario, galaxy clusters would be pulled apart, then galaxies, then solar systems, then planets, then atoms themselves, as space expands so rapidly that no force can hold structures together. Current observations do not favor this outcome, but they cannot completely rule it out. Another possibility is that dark energy might decay or transform into something else. If dark energy is a quantum field rather than a cosmological constant, it might eventually transition to a lower energy state, potentially triggering a new phase of cosmic evolution or even a recollapse of space. These scenarios remain highly speculative and are not supported by current evidence, but they illustrate that the universe's ultimate fate is not yet entirely certain. What is certain is that the accelerating expansion driven by dark energy fundamentally shapes the universe's trajectory. The cosmos will grow larger without bound. Structures beyond our local gravitational neighborhood will become forever unreachable, and the universe of the far future will be a vast, dark, cold expanse bearing little resemblance to the vibrant cosmos we observe today. The universe's size is not approaching some final value, but is instead on a path toward indefinite, accelerating growth. Measuring the immeasurable. Determining the size of the universe requires measuring distances across cosmic scales, a task that pushes the limits of human ingenuity and scientific methodology. The techniques astronomers use to gauge these vast distances form what is called the cosmic distance ladder, a series of methods that build upon each other to extend our measurements from nearby stars to the edges of the observable universe. The first rung of this ladder is direct geometric measurement using parallax. As Earth orbits the Sun, nearby stars appear to shift slightly against the background of more distant stars, just as a nearby tree appears to move against distant mountains when you drive past it. By measuring this angular shift and knowing Earth's orbital diameter, astronomers can calculate the distance to stars through simple trigonometry. This method works well for stars within a few hundred light years, but becomes impractical for more distant objects, as the angular shifts become too small to measure accurately, even with our most precise instruments. The next rung involves standard candles, objects whose intrinsic brightness is known. If you know how bright an object truly is and can measure how bright it appears, you can calculate its distance. The inverse square law tells us that brightness decreases with the square of distance, so an object 4 times farther away appears 16 times dimmer. Cepheid variable stars serve as crucial standard candles for measuring distances to nearby galaxies. These pulsating stars have a well-established relationship between their pulsation period and their intrinsic luminosity. A cepheid that pulsates more slowly is inherently brighter than one that pulsates quickly. By measuring a cepheid's period and apparent brightness, astronomers can determine its distance. Edwin Hubble used Cepheids to prove that Andromeda lay far outside the Milky Way, and they remain essential for calibrating cosmic distances to this day. For more distant galaxies, too far for individual Cepheids to be resolved, astronomers turn to Type Ia supernovae. These stellar explosions occur when a white dwarf star accretes enough matter from a companion to exceed a critical mass threshold and undergoes thermonuclear explosion. Because this threshold is always the same, about 1.4 times the mass of the Sun, Type Ia supernovae reach nearly identical peak brightnesses, making them excellent standard candles visible across billions of light years. The Tully-Fisher relation provides another distance measurement method for spiral galaxies. This empirical relationship links a galaxy's rotational velocity, measured from the Doppler shifts in its spectrum, to its intrinsic luminosity. Faster rotating galaxies are more luminous. By measuring rotation speed and apparent brightness, astronomers can deduce distance. For the most distant galaxies, astronomers rely on redshift, the stretching of light waves by cosmic expansion. The amount of redshift indicates how much the universe has expanded since the light was emitted, which in turn reveals the distance. However, converting redshift to distance requires knowing the expansion history of the universe, which depends on the amounts of matter and dark energy present. This introduces some uncertainty, though our measurements of these quantities have become increasingly precise. The cosmic microwave background provides an independent anchor for the distance scale. Careful analysis of temperature fluctuations in this radiation reveals characteristic patterns imprinted when the universe was 380,000 years old. By comparing the angular size of these patterns to their known physical size at that epoch, astronomers can determine the geometry and expansion history of the universe, effectively measuring the distance to the cosmic microwave background itself at 46.5 billion light-years. Gravitational lensing offers another powerful distance measurement technique. When light from a distant galaxy passes near a massive foreground object like a galaxy cluster, the gravity of the foreground object bends the light, creating multiple images or arcs of the background galaxy. By analyzing these distortions, astronomers can measure the masses of the lensing objects and calculate distances to both the lens and the background source. Recent years have brought exciting new methods. Gravitational waves from merging black holes or neutron stars provide standard sirens, similar to standard candles, but using gravitational radiation instead of light. When a neutron-star merger produces both gravitational waves and electromagnetic radiation, astronomers can measure the distance from the gravitational wave signal and the redshift from the electromagnetic spectrum, providing an independent measurement of cosmic expansion. Each of these methods has uncertainties and systematic errors that must be carefully characterized. The cosmic distance ladder is only as strong as its weakest rung, and errors can propagate as measurements extend to greater distances. This has led to ongoing debates about precise values for parameters like the Hubble constant, with different measurement techniques yielding slightly different results. One persistent puzzle is the Hubble tension, a significant disagreement between measurements of the Hubble constant using the cosmic distance ladder based on nearby observations versus measurements based on the cosmic microwave background. The distance ladder approach yields a value around 73 kilometers per second per megaparsec, while the cosmic microwave background analysis gives about 67. This 6% discrepancy may indicate new physics or subtle systematic errors in one or both methods. Despite these challenges, the cosmic distance ladder has enabled remarkably precise measurements of the universe's size and age. We know the observable universe is approximately 93 billion light-years in diameter, with an uncertainty of only a few percent. We know the universe is 13.8 billion years old, with an uncertainty of only about 20 million years. These achievements represent one of the great triumphs of modern observational astronomy. The techniques continue to improve. The James Webb Space Telescope, launched in 2021, is detecting Cepheids and other standard candles in galaxies far more distant than Hubble could reach, potentially resolving the Hubble tension. Future missions like the Nancy Grace Roman Space Telescope will survey supernovae across vast volumes of space, further refining our understanding of cosmic expansion. Measuring cosmic distances is not merely an exercise in precision. It reveals the fundamental nature of space and time, tests our understanding of gravity and cosmology, and allows us to map the universe's structure and evolution. Every measurement extends our vision, bringing the full scale of the cosmos into sharper focus and revealing just how large the universe really is. The multiverse hypothesis. As we push the boundaries of our understanding about the universe's size, we encounter theoretical frameworks that suggest our observable universe, vast as it is, might be just one among countless others. The multiverse hypothesis, while speculative and controversial, emerges naturally from several independent areas of modern physics and cosmology, offering a perspective in which the question of the universe's size becomes almost incomprehensibly larger. The concept of a multiverse arises most directly from the theory of eternal inflation. Recall that our universe underwent a brief period of exponentially rapid expansion in its first moments. Inflationary theory, developed in the 1980s by Alan Guth, Andre Lind, and others, explains many observed properties of our universe, including its remarkable uniformity and geometric flatness. But the same quantum field that drove inflation in our region of space might still be inflating elsewhere. In the eternal inflation scenario, once inflation begins anywhere, it continues indefinitely in most regions. Quantum fluctuations occasionally cause the inflaton field, the hypothetical field driving inflation, to drop to a lower energy state in localized regions. When this happens, inflation stops in that region, and a hot, dense state like our Big Bang forms. This pocket universe then expands and cools, potentially forming galaxies and stars just as ours did. But surrounding this bubble, inflation continues, and more bubbles constantly form. This process has no end. Inflation is eternal to the future, constantly creating new pocket universes within an ever-expanding inflating space. Each pocket universe has its own Big Bang event, its own history, potentially its own laws of physics or values for fundamental constants. Our observable universe would be one such bubble, perhaps 93 billion light-years in diameter or larger depending on details, but the total multiverse would be vastly, perhaps infinitely, larger. The spaces between bubble universes are expanding so rapidly due to ongoing inflation that no signal from one bubble could ever reach another. Each bubble universe is causally disconnected from all others, making them effectively separate universes despite being part of the same underlying multiverse structure. We could never observe these other universes even in principle, as no light or gravitational wave or any other signal could traverse the inflating space between bubbles. String theory suggests another form of multiverse. In string theory's mathematical framework, the fundamental constants of physics and even the number of spatial dimensions might vary in different regions of space. The landscape of string theory comprises perhaps 10 to the power of 500 different possible vacuum states, each corresponding to a different set of physical laws and constants. If eternal inflation is correct, different bubble universes might settle into different vacuum states, creating a vast multiverse in which every possible set of physical laws is realized somewhere. This raises profound questions about why our universe has the properties it does. Why is the cosmological constant so small but not exactly zero? Why are the masses of fundamental particles the values they are? Why does our universe have 3 spatial dimensions? In a multiverse framework, these questions might have anthropic answers. We observe this particular universe because it has properties compatible with the evolution of complex structures and life. Universes with very different constants might not form stars, or atoms, or any structures capable of supporting observers. The many worlds interpretation of quantum mechanics proposes yet another type of multiverse. In this view, every quantum measurement causes the universe to split into multiple branches, each representing a different outcome. Every time a particle's wave function collapses, every time a quantum event occurs, the universe bifurcates into versions where each possible outcome is realized. The number of these parallel universes would be staggeringly, perhaps infinitely, large, with new universes being created every instant. The mathematical universe hypothesis, proposed by cosmologist Max Tegmark, suggests that all mathematical structures exist as physical realities. In this most expansive conception of the multiverse, every consistent mathematical framework describes an actual universe somewhere in a vast ensemble of all possible realities. This would include universes with different numbers of dimensions, different physical laws, perhaps even different mathematical structures underlying their physics. Critics of multiverse theories argue that these ideas are not scientific because they make no testable predictions. If we can never observe other universes, never gather data about them, never perform experiments to confirm or refute their existence, then the multiverse hypothesis is metaphysics rather than physics. Proponents counter that the multiverse emerges naturally from well-tested theories like inflation and quantum mechanics, and that indirect evidence might be obtainable, such as the distribution of constants in our universe or possible collision signatures if bubble universes happen to collide in the early cosmos. Some observations have been proposed as potential multiverse evidence. The cosmic microwave background contains anomalies, including a cold spot and unexpected correlations at large scales, that some researchers suggest might be signatures of a collision between our bubble universe and another in the distant past. Most cosmologists remain skeptical of these interpretations, favoring more conventional explanations, but they illustrate how the multiverse concept, despite being seemingly untestable, might still leave observable traces. The multiverse dramatically changes the answer to the question of how big the universe is. If eternal inflation is correct, the total multiverse is infinitely large, constantly growing as inflation continues and new bubble universes form. Our observable universe becomes an infinitesimal speck within a single bubble universe, which itself is an infinitesimal speck within an infinite multiverse. The scale becomes literally boundless, extending beyond any finite number into true mathematical infinity. Moreover, if the mathematical universe hypothesis or similar ideas hold true, then we must expand our conception beyond physical space entirely. The multiverse would encompass not only all possible configurations of matter and energy in three-dimensional space, but all possible mathematical structures, all possible dimensionalities, all possible physical laws. The question of size becomes almost meaningless in such a framework, as we are no longer talking about spatial extent, but about the cardinality of mathematical possibility. Whether the multiverse exists remains one of the most controversial questions in fundamental physics. It represents the frontier where cosmology meets philosophy, where scientific method faces its potential limits, and where our conception of the universe must either expand to encompass possibilities almost infinitely larger than we imagined or remain confined to the observable cosmos we can actually study. For now, the multiverse remains a compelling theoretical possibility, emerging from serious physics, but not yet confirmed by direct observation. It represents the ultimate extension of the question of how big the universe is, suggesting the answer might be not just large, not just unimaginably vast, but quite possibly infinite. The mystery of what we cannot know. As we have explored the dimensions of the universe, we have encountered not only vast distances and enormous structures, but also fundamental limits to what can be known. These limits are not merely technological, issues that better telescopes or more sophisticated instruments might overcome, but rather represent absolute boundaries imposed by the nature of space, time, and light itself. The most obvious limit is our cosmic horizon, the boundary beyond which light has not had time to reach us since the Big Bang. This horizon is not a wall or edge, but simply a limitation of observation. As time passes, this boundary should expand, allowing us to see light from increasingly distant regions. 1 trillion years from now, if humanity or its descendants still exist, they should in principle be able to observe regions that are currently beyond our view. However, the accelerating expansion driven by dark energy complicates this simple picture. While the particle horizon, the boundary defined by light travel time, continues to expand, there is another horizon called the event horizon that is shrinking in moving coordinates. The event horizon represents the boundary beyond which events happening now will never be observable to us in the future, no matter how long we wait. Because dark energy causes expansion to accelerate, galaxies beyond a certain distance are receding from us faster than light can approach us, even though space itself is expanding. The cosmic event horizon currently lies at about 16 billion light-years away in proper distance. Galaxies beyond this horizon are effectively lost to us forever. We can see them now because we are observing their ancient light emitted when they were within the horizon, but events occurring in those galaxies today will never be observable. The light from those current events will never overcome the expansion of space to reach us. This creates a peculiar situation where our observable universe contains galaxies we can see, but can never receive new information from. We observe their past, but are forever cut off from their present and future. As time goes on and expansion continues, more and more galaxies will cross the event horizon and disappear from our future observations. The observable universe, in terms of the number of galaxies it contains, will actually shrink even as the particle horizon expands. There are also limits imposed by quantum mechanics and information theory. The Bekenstein bound sets a maximum amount of information that can be contained within a given region of space. This limit is related to entropy and suggests that the universe, even if infinite in extent, might contain only a finite amount of information within our observable bubble. Some interpretations suggest this might limit what structures can form and what complexity can exist within our cosmic horizon. The holographic principle, emerging from black hole thermodynamics and string theory, proposes that all the information contained in a volume of space can be described by information encoded on the boundary of that region. In the context of cosmology, this suggests that our three-dimensional observable universe might be entirely described by information on a two-dimensional cosmic horizon. If true, this principle would have profound implications for the nature of space and the limits of possible knowledge. Another fundamental limitation arises from the quantum nature of spacetime itself. Below a certain scale called the Planck length, approximately 10 to the power of -35 meters, the concepts of space and time as we understand them break down. Quantum fluctuations become so intense that the smooth fabric of spacetime dissolves into a foam of quantum uncertainty. We cannot in principle measure distances or times smaller than Planck scales, representing an ultimate limit to observational precision imposed by nature itself. These quantum limits also extend to cosmic scales. If we try to measure the universe's properties with infinite precision, we run into Heisenberg uncertainty principles that prevent us from knowing both the exact expansion rate and the exact energy density simultaneously. There are fundamental limits to how accurately we can determine cosmic parameters, no matter how good our instruments become. The finite speed of light creates another sort of limitation. When we observe distant galaxies, we see them as they were billions of years ago. We can never see their current state. The most distant observable objects appear to us as they were when the universe was very young, but those objects have evolved significantly in the intervening billions of years, and we have no way to observe their present condition. Our observations are always of the past, never of the simultaneous present across cosmic distances. This peculiarity of observation means that our map of the universe is fundamentally historical rather than instantaneous. We see a nested series of time slices, nearby objects nearly as they are now, more distant objects as they were in the progressively more distant past. The observable universe is not a snapshot of a single moment, but rather a deep time exposure, a view that combines information from across billions of years of cosmic history. There are also practical limits to what we can measure. The cosmic microwave background, while extraordinarily informative, represents an opaque barrier to observation. Before the universe became transparent at 380,000 years after the Big Bang, photons could not travel freely, so we can never use light to directly observe earlier epochs. Neutrinos from the first second might in principle be detected, and gravitational waves from cosmic inflation could theoretically be measured through their imprint on the cosmic microwave background polarization, but these represent the absolute earliest epochs we could ever hope to probe. Furthermore, there are questions that may simply have no answer, even in principle. If the universe is infinite, we can never verify this through observation, as we can only ever observe a finite region. If a multiverse exists beyond our bubble universe, we can never confirm it through direct detection, as no signal from another bubble can reach us across the inflating space between universes. Some truths about reality, if they are truths, may be permanently beyond human knowledge. The nature of dark energy and dark matter, which together constitute 95% of the universe's content, remains mysterious despite decades of observations and experiments. We detect their effects, but cannot directly observe these substances. Whether we will eventually understand their nature, or whether they represent fundamental mysteries that lie beyond our capability to solve, remains an open question. Similarly, the initial conditions of the universe, the state of affairs in the first moments after or during the Big Bang, might be fundamentally inaccessible. If inflation occurred, it wiped clean almost all information about what came before, like a cosmic reset button. Asking what preceded inflation, or what caused the Big Bang, might be asking questions that have no meaningful answers, as time itself emerged from the Big Bang and may have no existence before that moment. These limits define the boundary between knowledge and mystery, between what we can discover through observation and experiment and what will forever remain speculation. They remind us that for all our sophisticated instruments and elegant theories, there are questions we cannot answer, observations we cannot make, and truths we cannot verify. The universe keeps its deepest secrets, maintaining a realm of permanent mystery at the heart of cosmic existence. Yet far from being discouraging, these limits make the knowledge we have gained all the more remarkable. Through human ingenuity, mathematics, and the careful application of scientific method, we have measured the universe to extraordinary precision, mapped its structure across billions of light years, traced its history across billions of years, and developed theories that explain the nature of space, time, matter, and energy with stunning accuracy. We have pushed our understanding to the very boundaries of what is possible to know, and in doing so, we have revealed just how large the universe is and how small we are within it. Contemplating infinity and our place within it. As we reach the end of our journey through cosmic scale, we find ourselves confronting questions that transcend mere measurement and enter the realm of philosophy and meaning. The universe, whether 93 billion light-years in diameter or vastly larger, whether finite or infinite, challenges us to reconsider our place within it, and to grapple with what it means to exist in such an incomprehensibly vast cosmos. The sheer scale of the universe induces a kind of existential vertigo. We live on a planet 8,000 miles in diameter, orbiting a star that is one of perhaps 400 billion in our galaxy, which is itself one of at least 100 billion, and perhaps 2 trillion galaxies in the observable universe. Each of those galaxies contains hundreds of billions of stars, many of which likely host planets. The number of worlds in the observable universe exceeds human comprehension, and yet this observable region might be an infinitesimally small fraction of the total cosmos. From one perspective, this scale can seem to diminish human significance to the point of absurdity. How can our lives, our civilizations, our entire history matter in a universe so vast? If the cosmos extends trillions of light years beyond what we can observe, if a multiverse encompasses infinite bubble universes, each larger than we can imagine, then our Earth becomes less than a grain of sand on all the beaches of all the worlds of all the galaxies combined. Yet there is another way to view our cosmic situation. We are not separate from the universe, but part of it, made of atoms forged in stellar furnaces, animated by the same physical laws that govern galaxies and govern quantum fields. We are the universe's way of knowing itself, complex arrangements of matter that have become conscious and can contemplate cosmic immensity. The fact that creatures on one small planet can measure the universe, can trace its history from the Big Bang to the present, can predict its future across trillions of years, represents something profound and precious. The universe's vastness also highlights the extraordinary rarity and value of complexity. While matter fills the cosmos, most of it exists in relatively simple forms, hydrogen and helium gas, stars burning their fuel, rocks and ice and dust. Complex chemistry requires special conditions, planetary surfaces or stellar atmospheres or interstellar clouds. Life, as far as we yet know, might be exceedingly rare, requiring a remarkable chain of circumstances to emerge and evolve. Consciousness and intelligence might be rarer still. If this is so, then despite occupying an infinitesimal fraction of space, living, thinking beings represent an emergence of complexity and order that is cosmically significant. The billions of galaxies contain primarily simple structures following simple physical laws. But here, on at least one world, matter has organized itself into systems capable of art and science, love and philosophy, capable of understanding the very universe that gave them birth. This is no small thing, regardless of the cosmic scale. The possibility of extraterrestrial intelligence adds another dimension to these contemplations. In a universe with hundreds of billions of galaxies, each containing hundreds of billions of stars, the sheer number of planets must be staggering. Even if life is rare and intelligence rarer still, the vast number of opportunities suggests there should be many worlds where consciousness has emerged. Whether we will ever detect these other civilizations, whether they are common or virtually unique, remains unknown. If intelligent life is common, we are part of a vast cosmic community separated by distances so great that communication across interstellar or intergalactic space becomes impractical or impossible. Each civilization develops in isolation, creating their own art and science, grappling with their own existential questions, perhaps wondering as we do whether they are alone. If intelligent life is rare, then each instance becomes precious beyond measure, an isolated island of consciousness in a vast, unconscious ocean. The finite speed of light and the vast distances between stars impose a kind of cosmic loneliness. Even if technological civilizations exist in our own galaxy, the thousands of light years separating us from any plausible neighbors mean that meaningful conversation becomes impossible. A message sent to a civilization 1,000 light years away will not receive a response for 2,000 years. Civilizations rise and fall on shorter timescales. We are, at least for now and perhaps forever, isolated by the sheer scale of space itself. This isolation is amplified by cosmic expansion. Civilizations in distant galaxies are receding from us, many at speeds exceeding light. We will never contact them, never know of their existence except as ancient light from their past. As expansion accelerates, even our galactic neighborhood will eventually become isolated, cut off from the rest of the universe by an insurmountable gulf of expanding space. These contemplations return us to the question with which we began. How big is the universe really? We have seen that the observable universe spans 93 billion light years, containing hundreds of billions to trillions of galaxies. We have learned that the total universe likely extends far beyond what we can observe, perhaps thousands or trillions of times larger, perhaps infinite. We have encountered the possibility of a multiverse, in which our entire cosmos is one bubble among countless others. The answer to our question depends on which universe we mean. The observable universe has a definite, measurable size. The total universe might be vastly larger or infinite. The multiverse, if it exists, encompasses realms beyond our ability to observe or perhaps even to meaningfully describe. Each frame of reference gives a different answer, from merely enormous to literally infinite. What remains constant across all these scales is the remarkable fact that we can ask the question at all. Through centuries of observation, experimentation, and theoretical development, humanity has reached out across cosmic distances and backward across cosmic time to measure and understand the arena in which we exist. We have discovered that the universe is far larger, far older, and far stranger than our ancestors imagined. We have learned that we live in an expanding cosmos, that matter is mostly dark and invisible, that space itself is filled with a mysterious energy pushing the universe to accelerate toward an increasingly cold and empty future. We have also learned humility. The more we discover, the more we realize how much we do not know. Dark matter and dark energy remain mysterious despite decades of study. The beginning and ultimate fate of the universe involve physics we do not yet fully understand. The possibility of a multiverse raises questions that may be permanently beyond our ability to answer. Each discovery opens new mysteries, new questions, new frontiers of ignorance. Yet this expanding circle of knowledge, even as it reveals larger circles of ignorance beyond, represents genuine progress in human understanding. We have measured what earlier generations could only speculate about. We have tested theories to extraordinary precision. We have built a mathematical framework that describes the universe from quantum scales to cosmic scales with remarkable accuracy. We know more about the universe now than ever before in human history, and our knowledge continues to grow. The universe is not just big. It is a nested hierarchy of scales, from the quantum foam of the Planck length to the cosmic horizon 46.5 billion light-years away, potentially extending to infinity beyond. It is a structure with history, evolving from a hot, dense beginning to a vast, cool expanse. It is a dynamic system, expanding and accelerating, changing its character over billions of years. It may be one among countless universes in an infinite multiverse, or it may be all that exists. How big is the universe really? It is at least 93 billion light-years across. It is probably many times larger, perhaps infinitely large. It might be embedded in an even larger multiverse of bubble universes. It contains at least hundreds of billions of galaxies, each with billions of stars, an amount of matter and space that exceeds our ability to fully comprehend. It has existed for 13.8 billion years and will continue expanding for trillions of years to come, perhaps forever. But beyond these numbers and measurements, the universe is also whatever we make of it. It is the arena for our existence, the context for our lives, the grand stage upon which the human drama and all of life on Earth unfolds. It is both humbling and empowering, diminishing us to insignificance while simultaneously demonstrating that insignificant beings can nevertheless understand cosmic vastness through reason and observation. As we gaze out at the night sky, at the distant lights of stars and galaxies scattered across space, we see not just distant objects, but a cosmos rich with history and structure. Governed by physical laws we have learned to describe with mathematics, extending beyond our vision to regions we can only infer and imagine. We see a universe that is, in the deepest sense, our home, the only place in all the vast cosmos where we know for certain that matter has organized itself into living, thinking beings capable of asking how big it all really is. The universe is as big as our ability to measure and our capacity to imagine, and both continue to expand with each new discovery. It is a frontier that perpetually recedes before us, always offering new questions, new mysteries, new wonders to explore. And in that sense, the universe's size is not merely a number but a challenge and an invitation, calling us to continue the great adventure of exploration and understanding that defines us as a species. In the end, perhaps the most important thing about the universe's size is not the specific measurements, but what those measurements reveal about the nature of reality and our place within it. The universe is vastly larger than we are, vastly older than human civilization, vastly more complex than any single mind can encompass. Yet we are part of it, connected to it through every atom in our bodies, related to stars through shared physical laws, inheritors of a cosmic history that stretches back to the first moments after the Big Bang. We began this journey by asking a simple question: how big is the universe really? We have seen that the answer involves observable horizons and expansion rates, dark energy and cosmic acceleration, structures spanning billions of light years and theoretical multiverses beyond all measurement. We have encountered distances that light takes billions of years to cross, numbers so large they lose meaning, and concepts that challenge our deepest assumptions about space and time. The universe is very big indeed. It may be the biggest thing there is, or it may be one among infinite others. Either way, it is the stage for everything we know and everything we can ever know. It is both the context that makes us insignificant and the arena that makes our significance possible. It is home to at least one world where conscious beings have emerged and learned to measure cosmic distances, to trace cosmic history, and to ponder their place in the grand scheme of existence. As you drift off to sleep tonight, perhaps you will carry with you some sense of this cosmic scale, some appreciation for the vast arena of space and time in which your life unfolds. The stars you see above you, those distant points of light, are part of a galaxy that is part of a local group, that is part of a supercluster, that is part of the cosmic web that fills the observable universe, which might be only a tiny fraction of the total cosmos. You are small, yes, but you are also part of something incomprehensibly large. You are temporary, living for mere decades in a universe that will exist for trillions of years, but you are also part of a continuous chain of existence stretching back to the Big Bang itself. You are made of atoms forged in stellar cores, connected to the cosmos through physics and chemistry, capable of understanding the universe that created you. The universe is 93 billion light-years across, and probably far larger. It contains trillions of galaxies and more stars than grains of sand on all of Earth's beaches. It has existed for 13.8 billion years and will continue far into the future. It is expanding, accelerating, evolving, and it is, in ways both literal and metaphorical, our home. That is how big the universe really is. Vast beyond imagining yet comprehensible through human reason, distant beyond reaching yet connected to us through every atom and every force. And with that thought, with this journey through cosmic scales complete, we return to our small blue planet, our brief lives, our everyday concerns, carrying with us perhaps a slightly larger perspective, a slightly deeper appreciation for the remarkable universe in which we find ourselves. The cosmos awaits in all its vastness, but for now, here in this moment, this is enough. If you enjoyed this journey through the cosmos and want to explore more mysteries of space and time with Quiet Cosmos, please take a moment to like this video and subscribe to the channel. Your support helps us continue creating these deep dives into the universe's greatest questions and most awe-inspiring phenomena. Until next time, keep looking up at the stars and wondering at the magnificent scale of everything that exists. Good night, and sleep well under the vast canopy of the cosmos. You have reached the end of the document.